I will be able to show you that actually the question about alien intelligence relates to some interesting moral philosophy questions, as well as, of course, an awful lot of very fun astronomy questions about technology and the ultimate human destiny. All right. So, well, there is an abstract which sounds interesting. The real, well, maybe you saw it on Facebook, maybe you didn't, but generally, the Fermi paradox is a misnomer. A lot of people like to call it a paradox because paradox is a fancy word that implies a deep conundrum. And yes, there is a deep conundrum. The paradox is where you have a contradiction of some kind. Two things that simultaneously can't be true. What Fermi actually asked at that lunch somewhere in the early 1950s was, where are they? And they realized that there is an interesting problem. If we think there is life in the universe, shouldn't we be seeing signs of it? Apparently the discussion started with some jokes about aliens stealing the waste paper baskets of New York. There was a cartoon about it in some newspaper. And then the collected geniuses started to discuss it. And according to some versions of it, this lunch discussion actually led to some pretty interesting mathematical discussion. According to others, it was completely unmemorable. It's very likely that none of the participants actually remembered what was going on. But over the years, Fermi may have become attached to this question about alien intelligence. And especially that there seems to be, it's not a proper paradox, at least a conflict between, on one hand, an enormous planet where there could be a lot of life, and some of it could be intelligent and do stuff that we would notice, and the fact that we're not noticing any of those goings on. As I'm going to show later, there is also a matter of time. The amount of time it took for us humans to go from mildly intelligent monkeys to the man on the moon was fairly short by any biological or geological time scale, and very short compared to the astronomical time scales. Hence, that seems to also suggest that, wait a minute, why haven't others come before us? Why is Earth not a parking lot for alien flying saucers? And this, of course, leads to a lot of very interesting big questions. So one aspect is, of course, very enjoyable. It's by its nature utterly interdisciplinary. It's also slightly disappointing because we haven't, and a lot of people are making really flaky and hand-wavy arguments about it, which scares off the sober-minded people. For the rest of us, of course, this is great fun. It's a good playground. But I'm hoping to show that we can actually apply a little bit of thinking and modeling to, if not answer Fermi's questions, at least show that whatever the answer is, it's going to be darn interesting. So typically throughout the literature on alien intelligence, people have been trying different attacks or different approaches to that. The first obvious one is, no, there are no aliens around. And the simplest assumption would be, yeah, we're extremely lucky. We might even be totally unique in the entire universe. Then, of course, there is an interesting, fairly new idea, and I'm going to get back to why this is surprisingly new, that we just happen to be the first intelligent species to crawl up on the shores of the universe. If we don't do anything, eventually we're going to the others, but we're here first. We got the chance to decide what the future is going to do. Then there is a scary scenario, of course, that intelligence is actually fairly short-lived and never amounts to much. Then there is another set of arguments saying that, yeah, there are aliens, but we do not see them. And if you're real optimistic, it's just because we humans are so limited. Oh, our radio telescope hasn't scanned the skies well enough, but actually there's a galactic club out there just waiting to send us the introductory messages once we found the right frequency. It might also be that, well, it's very hard to transmit messages or do anything over large distances. And then we have a slightly more pessimistic scenario as well. Aliens might be alien things, and we might not be able to notice that. And then there is, of course, the more paranoid thing. They're here. Maybe right in this room. Right now. Yeah. And at this point, of course, people get really uncomfortable, especially at academic conferences, because this is starting to sound silly. But as I'm going to argue, actually, this is something one should take surprisingly seriously. It's not from the X-files flying saucer perspective, but from other perspectives which might actually be far more scary. But let's jump into this. So the original approach in the search for extraterrestrial intelligence community was, let's listen for messages. So they put up telescopes and they did various surveys and didn't come up with very much. Then the next generation of SETI researchers started following an idea that was originally kind of pointed out by Nikolai Kardashev, the Russian astronomer, that, well, even if we're not deliberately trying to tell us something, we might notice it. If you watch the Earth at night, you're going to be able to observe that there are a lot of lights, especially shining very brightly on sodium emission lines. That's, of course, not intended as any message to the aliens or astronauts. That's just a side effect of us humans wanting to have safe roads. So the idea is that sufficient advanced aliens ought to have sufficiently big noticeable images. So let's look for them. And this might be the activities like antimatter annihilation, if we have really advanced physics that should produce emission lines that we should be able to recognize. And we expect that maybe antimatter doesn't occur naturally. Some people even suggested at one point that the metal technetium, which doesn't, as far as they knew, if we dumped a lot of that into the sun, the emission lines would tell everybody that, okay, here is a technological thesis. Later, it turned out that there are sources of technetium in nature, so that wouldn't have worked. And you can imagine things like englobing a star in a Dyson shell to collect all its energy, which would produce a particular kind of heat emission spectrum, which you can again do. And people have been looking for it without much success. That doesn't mean, of course, that we covered everything. Meanwhile, the skeptics and the people who think that we might actually be alone, they counter with a very interesting argument, which is the colorization counter argument. Even if you think it's going to be very slow and expensive, and few people are going to want to do it to colonize across the stars, if species are sufficiently long-lived, they're going to spread quite widely. So you can assume essentially any expansion speed, and assume that as soon as the colonists arrive in a new system, it takes a long while to build a big civilization until somebody else starts wasting taxpayer money and sending off a few colonists. And you can easily show that, well, that's still going to colonize a galaxy between 10 or 100 million years. And if you're a bit of an ecological pessimist, which was very much in fashion in the 70s when these ideas were first discussed, of course, the population explosion would be driving things even more. Assuming that the aliens would be having the same problem as humanity was perceived to have, that we're increasing exponential in number, they would, of course, be building all sorts of arcs or whatever to go colonizing, and you would get a wave that would expand very rapidly. So this argument would suggest that the galaxy ought to be really colonized already. We should be seeing the light in the sky from the advertisements, and the Earth should be apart from it. Since that's not true, we should become conclude, arguably the people behind these arguments, we should assume aliens don't exist. One can also refine this argument by saying, well, maybe it's tough to sell an article of living, breathing, or whatever you aliens, but you could sell robots. Self-replicating robots was suggested by Dyson and in particular as a really effective way of colonizing the galaxy, or at least sending out probes to go everywhere, or even meet and shake robotic manipulator and tentacle with all the aliens. Essentially the same line of reasoning goes. Even a fairly slow starship can get across the galaxy very rapidly if you have refraction. All right. So, and you probably see this equation too, the Drake equation, which is among the most silly equations ever invented, but it's an equation. And this is actually an important aspect of many domains, because if you're just making a logical argument, that might actually be a very valid form of reasoning, and should actually be quite compelling. But people tend to overestimate the power of an equation. So Drake was using this as a kind of rough sketch of an argument. He was not really intending it to be used as much as it has been used. And it's kind of embarrassing to see how much the mystique of mathematics has caught people. But this allows us to put in some numbers and get the number out, and as we all know, numbers are true somehow. Deep in the heart of every academic, I think there is a Pythagorean waiting to come out. And the interesting problem here is, of course, first of all, why this particular equation? For example, that first factor R was originally the star formation rate. Essentially, how many new stars are coming into the galaxy. And it's a rate because the last factor is the lifespan of the average civilization. So you need to have a rate in order to divide a rate, the time unit over here. But a lot of later formulas have been messing up the units and, for example, added the number of, instead of using the number of stars in the galaxy. So quite a lot of versions of the Drake equation are actually completely wrong. The units don't match up, and people don't even care. That tells you something about the mystique of numbers. However, we can, of course, play around and plug in stuff. So I was looking up on Wikipedia the entry today and looked at what they claim is the original values for the Drake equation. I actually haven't checked the paper directly, so this might be wrong, but he seemed to have some amazingly optimistic values. It was suggested between 1 and 5 planets that could support life per solar system that has planets. One interesting thing is that he was more pessimistic than we currently are about the likelihood of planets, because planet formation at that time was, of course, not very well understood. We didn't have an exoplanet observation and the later models of planetary accretion. The fun thing is, as Drake plugs in his numbers, he gets a range between 2 civilizations, us and them, somewhere out there, and about 50 million, which would be a decent galactic cloud. One alien civilization per citizen of Britain. If we plug in the numbers suggested by various other entries in Wikipedia, we can get an even better range. It's kind of nice to get 27 orders of magnitude of uncertainty. That actually beats my own estimate of where Moore's law is eventually going to stop. I have only got 20 orders of uncertainty. So this one is even more amazing. And the reason is, of course, that in many ways we don't understand what these ratios of these fractions even are. For example, the assumption here that we need to look at the length of our time a civilization might be transmitting information, that's somewhat problematic. David Britt, the science fiction author, he also wrote a very, very good article in 1983 about the search for extraterrestrial life, where he pointed out that one can develop this much more detailed by looking at the colonization patterns. You can essentially extend that L into a model of how civilization spread through the universe. That complicates things, but it actually makes it much more useful. Unfortunately, you get even more free parameters to play around. So, can we actually say something useful about this? Well, over time, we actually been able to narrow down some of the parameters. The star formation numbers, I think, are relatively controversial. The number of planets, well, we're getting loads of very nice data from the Kepler probe, so we actually have a good idea about that. The fraction of life, intelligent life, technologies, we have no clue about. And the one about modeling is, of course, pretty much certain. So I'm going to be mainly looking at those and see what we can do about and how philosophers can help next week up even more. One interesting thing about the story about the search for extraterrestrial life is that the perspective has shifted. So when people started thinking about it in the 50s and 60s, it was back in good old days of space travel. So rocket ships, probably nuclear, would be going to the stars with a lone crew captain and a crew of both space explorers. Okay, that sounded a bit tricky to actually achieve, but at least the trend cursor suggested that nuclear rockets were feasible. As time went on and we got into the 60s and 70s, the nuclear rockets started to look a bit less impressive. That space shuttle thing we were discussing, it sounded nice, but it was not quite what would bring you to the stars. Meanwhile, people like Gerard K. O'Neill was looking at space colonization and actually pointing out something very subversive. Why do we need planets? If we colonize space, we might actually want to live in space directly by building orbital habitats. They're rotating to provide gravity and essentially as large as we want them, and making a very good use of mass rather than piling it on top of each other as a planet. So if that was true, then planets was no longer the really important thing for the alien civilization. They might start on planets So then we might go and live in space. That produces a somewhat different view of it. And later on, of course, both as the Romans fell out of our own space program, we started realizing that actually we might be sending out space probes that are much more robotic, much more smarter, and maybe much more small than the previous one, as ideas on automation and nanotechnology took hold. We got a very different view of what a space probe might be. I'm going to be spending some time on that later. Also, our astronomy has, of course, changed. So now we have loads and loads and loads of exoplanets, and they're not just normal planets, they're weird. So we found hot Jupiters orbiting very close to the stars. We found the terrestrial planets that seems to be so heavy that they are probably ocean worlds covered with tens of kilometers of water. There are plenty of really hot worlds out there, mostly, of course, because they're easy to detect with current methods. That would suggest that there exists an extreme number of very, very hot planets with multiple metal rains and other nasty stuff. But also things like gas giants in the light zone, which people completely disbelieved until the late 90s. And you could imagine moons of these gas giants, of course, being quite nice terrestrial worlds, although the gas giant itself is not warm enough to heat them up. They're all orbiting through the life zone of the star, which might actually mean that you could have a lot of inhabitable planets very close together. And then there are brown dwarfs. There might be quite a lot of warm, if not the stars, somewhere above the gas giant level, out there instead of space. There might actually be quite a lot of dark biospheres. The realization that there might be an ocean under the ice of the Europa again suggested that there might be very non-terrestrial worlds with life. Also, the data seems to suggest that Earth is not, it did not form among the earliest planets in the galaxy. It's actually a relatively late comet, which again is a bit scary from the Fermi question, because that would suggest that plenty of aliens wouldn't have had time to evolve in earlier planets. Meanwhile, we also have realized that our biology, well, is very extremophiles. It turns out that some really like radioactivity, some like extreme temperatures, and dear old E. coli can apparently survive and even thrive at a few 100,000 Gs of gravity. There have been some weird experiments of growing them at extreme temperatures. So that would suggest that even if you have a ridiculously heavy planet, you could at least have some life on that one. At the same time, we also notice that life seems to have appeared on Earth very early in its history, not too long after the surface solidified enough that you could have an ocean surface. And we have also started to notice that most of those traits we take pride in being typically human in our intelligence, we can actually find remnants or fragments of in other species. Tool use is actually fairly widespread. It's just that deliberate tool use where you save your tools for the next time and have kind of cumulative cultural accumulation of tool use. Well, that's a unique to us. But chimpanzees certainly make tools. And it's just that it's hard for them to transport them, since they tend to walk on their knuckles and then carrying a stone is uncomfortable. We see in various aspects of problem solving and simple aspects of language in other species. So this suggests that the difference between humans and other animals when it comes to intelligence is not that enormous. If one had the view that it was an enormous difference, then you might argue that the probability of intelligence might be very low. But now it seems like it might be much easier to jump there. Another interesting thing is the assumption built into the Drake equation. If you look at it, this is actually assuming that there's an equilibrium in the galaxy. Civilizations pop up, except for one and then disappear, and there's kind of a constant ratio. But actually, the galaxy is changing. There is this work by Lineweaver and others showing that there might be galactic lifespan. Even in the earliest stages of the galaxy, there was not much metal. Astronomers regard anything that's not hydrogen or helium as a metal, so solid metal. There was not enough metal to make planets. So that would preclude planet formation for a long while. And of course, living close to the galactic center means that you have a lot of dangerous supernovas and gamma ray bursts. So the argument is something like, yeah, the central regions are going to be uninhabitable, at least life won't emerge there because of all these explosions. And the metallicity is evolving over time and spreading from the interior outwards. So you get a kind of life zone where planets and life might live. Similarly, these ideas of civilization, well, if we start expanding and turning planets into parking lots or uplifting other species to become simple, it's not an equilibrium situation. You actually get a galaxy before intelligence and a galaxy afterwards. And of course, you can look really far into the future and start thinking about the end of the universe. Freeman Dyson, in his really classic paper from 1979, Life Without End, was looking at the limits of how far could life survive into the end of the universe if it was going to expand forever. And then, of course, over the last 20 years, more and more thinking about post-biological evolution has come into the foreground. Transhumanists have been eager thinking about ways of transcending biology. So if we could upgrade it to turn ourselves into software to run on computers or create artificial intelligence. And when you start adding that, you realize that it's not just life zones that matter, it's X zones, where technological systems or whatever comes after technology would exist. So there's a lot of things going on here that might actually change our perspective. And finally, we have this issue of existential risk. There might be things that out there that dangerous and wipe out civilizations. So these ones have changed a little bit on how we think about it. So there are a few principles we can use to think carefully. So one standard method is to assume that we're typical. We shouldn't assume that we're special in a particular way, and this has worked historically fairly well. At the same time, we have another countervailing principle, the anthropic principle. We are actually special. This place is special because we are here. These two are kind of opposed to each other. For example, you might argue that we should expect to find ourselves at a typical place in the universe. But our typical place in the universe is interstellar space. And there are very few seminars held in interstellar space. In fact, there are very few seminars held on planetary surfaces. After all, most of the volume of our planet is interior. And even most of the surface of Earth is inhospitable, not just to seminars, but to human life. 2/3 of the planet we will be drowning. So, actually, there is an interesting thing. The Copernican principle is a kind of maximum entropy principle. Don't assume very much information. But then you need to cut it down and point out, yes, but there has to be an observer. That requires a very peculiar environment. And this might be really tricky, of course, because we might actually be very peculiar observers. If we have rare events, then we should expect our surroundings to be a bit weird. Another important thing is, of course, that not everybody, both in terms of humans or aliens, will do the same thing. In general, diversity will tend to prevail unless there is some countervailing factor. But as we're going to see, this is a problem for many arguments about what aliens will do, because it requires them all to do the same thing. Just imagine if we all here had to do exactly the same thing. It's very likely that somebody wouldn't do it just for fun, or because his philosophy forbade it, or just because he forgot, or because something else. And then we have the countershapers that pointed out a very interesting thing. Besides the limit set by physical law, doesn't seem to be any natural sidescape of what civilizations do. Right now, we're kind of limited by just being present on Earth. But if we were to go out into space and start colonizing it, yeah, we were getting out of a bottleneck essentially. But there is no reason why a space civilization should be just 10 star systems, or 100, or 1,000, or 1,000,000, or a galaxy, or a galaxy cluster. The size scale seems to be limited only by some physical limits, like how much energy can you get rid of, how far can you communicate in a reasonable amount of time. Okay, let's see. So, the no aliens argument. The first one is, of course, that intelligence is short-lived. This would be really bad. And this is, of course, the main motivation why I'm researching this, because we want at the FHI to figure out existential threats and ideally do something about it. So the first risk is external disasters. And we have some inklings about cosmological threats, like gamma-ray bursts and supernova. And maybe they're more common in the past, but they're not a terribly big threat to our survival now. If we were to actually properly get out into space, or even have a somewhat sensible biological art program on the surface of Earth, we would be pretty safe from that. So in general, it seems like this external disaster thing, either we need a new kind of disaster that I never heard about, or it's actually not going to count it as an explanation. Basically, if you want to explain the Fermi paradox by no aliens, you need to have very intense common disasters. Then, of course, it might be more metaphysical or philosophical ones. Maybe there's something bad with intelligence. Maybe intelligence by nature is broken. And this is very poetic and makes good science fiction stories. It's much harder to estimate whether this is true. So back in the 80s, Carl Sagan, for example, he was very pessimistic about this because it was right at the tail end of the Cold War and nuclear winter seemed to be just around the corner. But, well, a nuclear war would be bad, but unless the nuclear winter will be serious, which is an interesting and open question, it doesn't seem like it would be likely to wipe out humanity. So it's actually slightly tricky to get this to work. However, the real problem might be that there is a risk, of course, that nobody can foresee. No civilization ever foresees, and then we just run headlong into it. So we would like to figure this out. And we can do that, of course, in a reverse manner. Let's look at all the other possibilities and see what they tell us about this possibility. Because if it seems like we have some other very good explanation, then maybe we don't need to worry about this. Okay, so the good news would be if aliens turn out to be really, really rare. Well, at least it would be good news for us as species, maybe sad news for the xenobiologists. The problem with this explanation is that we got plenty of planets, and life seems to have emerged very early on Earth. So that would suggest that it's fairly easy to get life, and we're not that different from the other animals. And to be honest, the step between agriculture and saying radio, it's not that long. It's just a few thousand years. That's absolutely nothing. And it seems like once you start getting a population to expand out of the Malthusian trap by having the extra calories for agriculture, the cumulative nature of having a culture was starting to build to itself. You can certainly imagine alien civilizations that never get technology. Maybe they live on a water world where it comes making tools, so they're not getting it anymore. But it seems unlikely that that would be true for all civilizations everywhere, that we're the only dry land civilization in the universe. So it seems like this step is also kind of tricky to get to work. Another one is, of course, that we might just be lucky first, but again, as I've been mentioning, it doesn't seem to be that lucky. One way where you can play around with this is the Panspermia hypothesis, suggested by Svante Arrhenius, the chemist and astronomer. The idea is that spores spread from life-bearing plants, other life-bearing plants, to soon-to-be life-bearing plants. So the idea here it might be that an asteroid splashes down on Earth and various gunk and goo or mossy rocks get thrown out into space. Most, of course, of the life on Earth's rocks will immediately die and get fried by ultraviolet radiation, but some bacteria are very, very resilient and might remain in the rocks. We know that some of the planets in the solar system are exchanging meteorites at a certain low rate, so it's not entirely inconceivable that a few spores from Earth have ended up on Mars, or vice versa if there was life on Mars. This leads to interesting things where we can actually, if it turns out that we don't find Mars, life on Mars, that's either Mars was never possible to have life on in the first place, but most likely it would also mean that Panspermia doesn't work there. So that would be evidence against it. Conversely, if there turn out to be a easy spread life, that would tell us something. I've been playing around, and I don't think I have time because you have answers to this, but I've been playing around with a bit of mathematical modeling of this. So basically, you can model the planets spread out in the universe. Planets with life will tend to produce a bit of spores, and they have a certain probability of infecting other planets. So what happens typically is that the number of planets without life grows over time as they form. Then one life-bearing planet starts spreading spores, and a sizable fraction of them become life-bearing. And you can, of course, twiddle these parameters to get a more software situation where it takes much longer. Now, the interesting thing is we can actually do a maximum likelihood modeling of this. So given that the Earth forms at a certain point in time and that the life arrives at a certain point, we can actually put that into the model and calculate different parameter values with probability of this working. We have one data point which just allows us to know that we should be somewhere along these curves. If we get another data point, we're going to be able to actually calculate where it is. So actually, even figuring out that there is definitely no life on Mars would probably help us figure out some of these parameters. But right now, this is a paper that has the story that is based on a single data point. But at least we got a little bit of information. We can roughly estimate that it would be extremely weird to find ourselves out here. If we found evidence for that, then we would know something important was going on. All right. Then come to the fun side. What about the indexable evidence? Well, there are obvious reasons why we might miss them. We might simply not have the right tools. It might actually be an interesting problem how to transmit to. I don't have the time to get into it, but it seems like there's a kind of game theory problem going on here. You can imagine humans wanting to send a signal to aliens. Where should we point our radio telescopes? Meanwhile, the aliens suffering under a limited budget are also wondering what to put their radio telescopes. So actually, where to send these signals, it turns into a very fun, continuous strategy game theory problem. And it turns out that depending on how advanced civilizations you try to listen for or send to, you should look at different parts of the sky. Essentially, if you believe in those galactic light zones, it seems like you should be aiming, if you think that you could transmit or hear some really powerful civilization, kind of along the galactic disk, along the light zone. If we're just looking for the primitive aliens just nearby, then we can kind of spread it out by the local stars. So there's some weird non-trivial stuff going on there. But again, this requires you to make certain assumptions about the energy balance. Similarly, there are a lot of practical questions. And this is, of course, where things get really fun. So I'm going to rush through a bit of work I've been doing with my colleague Stuart Armstrong about spanning the universe. So essentially, sending radio messages, although it seems easy, in practice it's very hard to send an update. It's much easier to go there and deliver the message person, or send a robot to deliver the message. So we were thinking, okay, those colonization scenarios, how far can we take them? What's the biggest colonization project you could actually get by physical law? So we did a bit of exploratory engineering with a slide stolen from Eric Drexler, who kind of been thinking about these issues of what can we say about technologies that don't exist yet, but are constrained by the laws of physics as we know them. We know certain technology cannot possibly exist because various physical laws are different, and the Altera stuff we don't know how to do. But if we could do it, we can still tell a bit about the performance. So we can assume, let's say, a civilization that's 1,000 years ahead of humans or so. And most likely, if nature can do it, we can do it too. Doesn't seem to be anything so far we found that was absolutely impossible. Usually it's mysterious until we figure out how to apply it, but then it's fairly straightforward. We're also very good at automating stuff, and we can automate building stuff. So that leads to this Kardashev assumption that we can actually scale things up. And most likely it's going to be the kind of physical resources. Okay, so we want to send probes really far. So Freeman Dyson, this idea about Dyson shell is a rather easy thing to do. We have already started. We have a few satellites in orbit around the sun that use a little bit of sunlight to power themselves. So the first step in building a complete Dyson shell around the sun. Maybe we're not going to ever do it, but in principle, if we just took the Soho satellite and multiplied it by a few trillion, we would have a Dyson shell. Solar collectors in orbit around the sun, they would get an awful lot of energy, of course. You can try to build a solid shell, which is suited for interesting reasons, and you can complicate things in fun ways. But the real question is, of course, how to actually build. Well, we have Mercury. And Robert Bradbury wrote a very nice little paper about planetary disassembly. So basically what you do is you get energy, you use that to mine stuff on the surface of Mercury, you push it up into orbit, you do some mass driver or something like that. Then you make solar collectors, which allow you to make more energy, get more energy and more mining equipment, etc. And then you repeat. And when you model this using various ridiculously conservative assumptions, it turns out that, yeah, you get exponential growth. It takes about 40 years until you completely wipe out your Mercury. And, well, we might, of course, start with asteroids because they're easier, etc. But Mercury was kind of convenient. It was young there. Okay. So basically, this shows that, yeah, just having replication of some kind and automation already allows you to mess with things actually on planetary scale in surprisingly short time scales. normally 40 years. That's about the time it takes for one of the outer planets to get a bit ahead of its orbit. But here you have Mercury kind of turning into a lot of solar collectors. The next step is, of course, what should the probes be? And again, I don't have that much time. There is some very fun work here by Bracewell and Freitas. Freitas have done an extremely conservative sketch of how to do it. And he was assuming a replication time of 500 years, most of the stuff that came through now getting fuel for gas giants. So we can look at very small biological replicators, and I think when we get to the size of an acorn, now I think we're in the right ballpark. It's a 1 gram object that can turn into a multi-ton object over a span of 2 decades. So in our case, it would of course probably be some nanotechnology thing, nuclear power, yes, nuclear power acorns. I love that idea. And then you would add a little bit robotics. So for example, you could put it on an asteroid surface, it would dig up stuff, essentially repeat the mercury thing, but now turn into whatever you want to fabricate. So that would be about 30 gram object that we estimate. It's not terribly sensitive. Then we get to the horrific rocket equation, and this is the relativistic version. This is my least favorite equation in all of physics. The problem with the rocket equation is that it tells you that you need essentially exponential amounts of reaction mass in order to get that velocity. This is why we don't want to actually have a rocket that accelerates in the traditional way and then slows down, because now you need to run it twice. And that's even worse, doubly exponential. So what we're thinking about is having a good launcher and driven by that enormous Dyson shell, and then you have a little rocket that slows things down. And again, I don't have the time to get into the details about how you might decide to do it. So we looked at the different version, a high-tech version using antimatter, that is about 3 kilograms small, a little fusion reactor thing on a few tons, over to a pretty hefty nerve rocket thing, probably bought from the Russians, and that is about 30 tons heavy. Then instead of just going using the split, which was again the assumption by the old people in the 70s and the 80s, which was kind of based on an inherent assumption that going through space is hard, and so you must make short turns. When you start thinking about the real, actually, once you're moving, it doesn't matter. It's nothing there, more or less. And that means that you can aim at something very remote. So we were looking at what happens if you actually just send out an awful lot of probes at the same time. And this turns out to have a lot of other interesting advantages too. Which, one is, of course, that the amount of time here, going from that galaxy to that galaxy straight, is going to be much faster than slowing down, building stuff here, accelerating it up, slowing down, building stuff here, accelerating. And also, if you're worried about having self-replicated artificial intelligence devices around, some people for some reason are, then there are fewer generations here where they might come up with stupid programming bugs or rebel or come up with better ways or better things to do with their lives. So, looking at all this, then you bundle it together, and then you get Stewart, who happens to be a mathematician, to solve the Friedman equation for the expansion of the universe, because there's also this nasty problem that the galaxies are kind of running away from us at a faster and faster speed. And you can actually calculate how much of the universe you could reach if you could send off probes at various high speeds. And it seems like, if we just reach 50% of light speed with these kind of probes, then we can get 130 million galaxies for us. That's a lot of galaxies. And with 99% light speed, then you can get about 5 billion galaxies. This is actually a surprisingly small part of the visible universe. There's a lot of galaxies we can observe that we will never ever be able to reach, no matter how fast rockets we build, simply because by the time they get to the point where the galaxy was, they're expanding away so much faster that the rocket will never catch up. You can even use this for a really weird form of deceleration of the rocket. So the rocket is actually going very fast at the start, but then as the universe expands, its relative speed goes down, so it will arrive at the galaxy at a very low speed. It takes a lot of time, of course, so we might be in a hurry because we might want to compete with aliens. But you can do it if you're energy conscious or want to have a pure elegance of it, or just want to solve a fun math problem. So, in this kind of scenario, it seems like actually waiting for a long time doesn't matter as long as you don't launch your rocket at very high speed. And then you can calculate. We need redundancy because space is not complete yet. There is a bit of dust out there. That is actually the limiting factor when you do this really carefully. Because if you run into a single speck of dust at 99% of light speed, that speck of dust explodes in a nuclear fireball, which is probably not very good for your little nuclear atom. So you want to have a redundancy. You send out several copies, and some of them blow up during the test. Or you try to develop some really clever shielding systems. Exploratory has some very amazing ideas on that. But we were kind of trying to do the crude, stupid approach. Yes, and loads of them. The interesting thing here is, of course, how long time does it take for our former Mercury, now Dyson shell, to launch the stuff? And the answer is, if we want to send out our fission probes, it will take about 7 minutes, assuming one copy per galaxy. Let's multiply by 10. Okay, 70 minutes, a bit more than an hour to launch all of them. If it's the antimatter one, then it would take 10 minutes to send 10 copies to every galaxy we can reach. If we assume that there's much bigger probes, we actually have those great 500-ton probes, now we're talking a few centuries. Still not very much on a galactic time scale. It may be a bit boring project to be keep watching. But that one is an afternoon. We're talking about that once everything is in place, colonizing the universe is pressing a button, waiting an afternoon, seeing a lot of things getting launched, and then wondering what to do with Dyson shell. That's now kind of pointless. Well, actually, I think we can find solutions. However, the main point is the cosmic scale approximation of it is 0. That we have colonized the universe in essentially no time. That's kind of cool. Okay, and this is fun because it makes the Fermi question really nasty. Philosophers love when limit problems works, not yet. So if you calculate how many, if we go back in time, in terms of billions of years before us, and if aliens have done the same thing, how many galaxies could they have reached? And vice versa, how many galaxies could have colonized us? And it turns out that, well, if the upstart had a 2 billion years head start, they could have at least 4 million galaxies could have reached us. The main reason is, of course, the universe was much smaller in those days, so it was easier to sort out stuff. There is a ridiculous first mover advantage in this kind of expanded universe. If they started 5 billion years ago and was being away at 99% light speed, about 400 million galaxies would have reached us. So we just managed to make the Fermi question a few million or a few billion times it works. Actually good. Okay, so alien nature is another way of saying it. I'm going to be very quick with this, but basically the argument is that aliens are weird. And we want to be able to understand their motives. So they're going to do weird alien things, so maybe they don't want to colonize. But that doesn't work because some aliens might, for weird alien motivation, want to colonize. And actually, it seems that a lot of them might have interesting technologies for that. So I think it's Saturday morning breakfast here I had a good point here. Even though some of them might be taken over by their own technology, well, if your robots rebel against you, now we have a robot civilization, which is just as bad to the Fermi question as having an alien civilization. One interesting line of argument might be that, well, those Dyson shells, what are they good? Well, you can put computers on them. You can run enormous simulations and virtual worlds. Just imagine having a civilization that could upload itself into World of Warcraft and spend the counterpart of the billions of man-hours on making it really amazingly good. Maybe what happened to civilization is that they develop more and more virtual worlds that are more and more addictive. And then they will move into them, and the only thing remaining in the universe are these World of Warcraft worlds or whatever they are, where the aliens are having a great, jolly good time. And they're very uninterested in communicating. This, of course, falls very much afoul of that assumption about the objective, because there are probably going to be some aliens who are religiously opposed to this and refuse to do it. A more refined version of this argument says that, yeah, but typically the trend is that people and life want to use resources more effectively. That means we use it faster, more energy efficient, shorter communication lengths. it's going to tend to kind of coalesce into smaller and smaller Dyson shells or Jupiter brains, and staying outside is going to be such an economic disadvantage that nobody will want to do that. Again, I think this doesn't work, because there are going to be so many alien Amish saying, I don't mind that I'm not going to be able to participate in your super cities. I'm going to be out here colonizing the world in the old-fashioned way with nanotechnology. You can model this in interesting ways, because you can imagine a certain percentage of these Amish, of course, eventually getting better ideas and moving in. And then, of course, some of their offspring also moving away, and some of their civilizations also kind of then getting grabbed in and turning into their own little types of ships. Generally, it seems like it's very hard to actually get the solution to get all the aliens to just get into the silent super civilization. They tend to really run off. So, I don't have much time, so I'm going to get to the final scary part of this, which is, of course, everyone here. So one classic idea is that, oh yes, the Prime Directive tells aliens that they're not supposed to mess with us, except that again we have this problem that there should be some alien Captain Kirks or teenagers that would like to mess with us. Another one, of course, very popular around the offices of the classroom is that, well, maybe we're already assimilated. And then there is the exercise as such. But there's another nice possibility, that's Berserkers among us. Remember those self-replicating machines? They're actually a very useful tool for a lot of things. Well, picking apart planets, colonizing the universe, killing off competitors, or keeping competitors from messing up the universe by building self-replicating systems. So I've been looking at this, and this is their preliminary results, but generally constructing berserkers seems to be a technological fairly easy. So they would be out there working, waiting for junk civilization to do something stupid like sending a radio message. And then they come at us. And technologically speaking, it would be fairly easy to do something that could attack a young civilization with overwhelming force. There's some interesting questions here about the warfare at the ultimate technological scale, so I don't have time to get into it. The interesting problem seems to be that if you imagine that there are different kinds of these automated probes out there, and you try to model the ecology as they were fighting each other, one of the conclusions I reached is that it's actually very hard to get a stable solution that actually fits with the universe we observe. The problem is actually quorum sensing, which is a term in biology about how bacteria and colonies notice how many bacteria there are. If you're out there hiding and being stealthy, it's very hard to know how many on your side are out there. And that means that reproduction becomes problematic. So typically, things tend to diverge and reduce all the resources, making copies of each other. And then we get a universe that's very much a parking lot rather than the apparently empty universe we see. So it seems like you can't have these quiet nemesis for several species. However, if one gets there first, remember that 5 billion years ago, we could actually colonize essentially everything and set up an interdict preventing anybody from doing it. Now, the nice thing about this is that they don't seem to be that antagonistic. If you think about human history, monkeys, sea monkey run, sea monkey play, sea monkey shape stone tools, sea monkey made fires, sea monkey domesticate crop, sea monkey run. At this point, it's very unlikely that any probe that was not sitting on Earth watching monkeys would notice anything weird ecologically going on. As the monkey rolls the wheels and alloying bronze and you construct buildings, well, maybe you could notice that if you had a satellite watching very carefully. Sea monkey do calculus, impossible to see. Sea monkey does steam engine, also rather tricky, not too different from alloying bronze. Sea monkey send temperate message. You need a really good antenna to notice what's going down both sides. Sea monkeys send radio signals. At this point, you can start detecting the monkeys at a certain distance. If you're far away and you want to wipe out monkeys and the radio signals before they go to space, now you need to start acting. So the step to the rocket was not that many decades. And we have added a few extra decades because we're lousy. Monkeys are lousy in administration and actually continue going to do it. That's another matter. So the point is, the fact that we haven't been wiped out somewhere around 1915 or so suggests that, well, if the probes are wrong, they're actually not interested in buttoning us up. We might get some interesting things happening if we try to send out a self-replicating probe. That's actually a very good test of whether there is some police probes preventing it. And if we're lucky, then we're going to get suddenly something showing up, telling us what the rules are. So if we're unlucky, of course, we might be a bit more rude and just blow us up. The problem is blowing up civilization is generally easier than communicating with it, because wireless is a kind of universal language. So, to conclude, we have a lot of hypotheses, and summing up where I think we end up after my look at this and this injection, is that, well, the science sky is telling us things. We actually have information. It's just that it's a bit hard to tell which of these possibilities there are. So one possibility is that the technology ceiling is much lower. We can't build those, and that needs to be rockets and isoshells and separate detectors. So, what's the point of being transhuman as that? Well, that's interesting also because it's kind of weird, because a lot of these technology we think we have is pretty good in that it could be done. Yeah, they're hard, but they're not anything impossible. Another totally interesting possibility is that there is a high existential risk. And it doesn't seem that we can easily rule that one out. The really interesting one from a philosophical standpoint might be that all advanced civilizations do the same thing. That's really strange. That would require some kind of evolutionary attractor that everybody, with no exception, ever falls into. And it's a good question whether that's a good thing. Some positively minded people might say, oh, they're all realizing what good is and are all following the rules and behaving very nicely. And that would be a pretty amazing result in meta-ethics, that all sufficient advanced civilizations figure out a certain ethical system. Of course, it might not be the right thing. It might be that all sufficient advanced civilizations become postmodernist relativists and never do anything useful ever again. But the weird thing is, in that case, if that was true, it would be, that kind of relative would be such an attractor that nobody could ever get out of it. It would be kind of one of those monkey traps, where the monkey tries to grab the food but then can't let go and can't get up. But nobody can ever figure out how to get out. That's also pretty weird. If there is a dominant old species that already kind of colonized the universe, and I had another discussion about why they might actually want to keep the universe looking a bit like the original, that has nothing to do with them being environmentalists, and more that they want to save the matter for the great era of harvest in 3 million years. Then we have to figure out what they like how to suck up. If we're simulations, well, we don't do much about that. It's been really interesting and having a really fun life to make sure we don't turn off the simulation. And finally, there is this weird possibility that we might actually be alone. In that case, we actually perhaps get the most uncomfortable and important information. Well, we are responsible for life and consciousness in the universe. We're it. We probably have a moral duty of some kind to spread that across the universe, and we better not mess up, otherwise this whole universe has kind of gone down the drain. So, that was my very brief story about the alien intelligence and why it actually matters in the philosophy department. Thank you.